Chapter 6, you've heard me allude to it. You've heard me talk about it. I've said, wait till chapter 6. Things get fun. Well, here we are, chapter 6. I hope it, efficiently frightened you of chapter 6 so that you'll give it the respect it deserves. I'm not joking when I say things you're going to learn in chapter 6 will carry on into Organic 2, Biochemistry, Organic 3, Biochem 2, Metabolism. This stuff's important. This is how organic chemistry works. We're going to learn 4 mechanisms. E1, E2, SN1, SN2. Don't bother writing them down. We're going to hear them again soon. Don't worry. If you understand those 4 mechanisms, there's not very many reactions that are different than that. There are a few, and they're subtle, and I'll show them to you. But those 4 basic mechanisms are so important that we're going to drive them home. Most reactions are variations on those themes. Not all of them, but most of them are. Okay? So let's try to hammer this in and keep it there. Classes of alkyl halides. There are 3 types. The first one you already know. Alkyl halides. A halide on an sp3 carbon. It's called an alkyl halide. There you go. You've already learned that one. Alkyl halides. sp3 carbon attached to a halogen. Doesn't have to be bromine. Any halogen, alkyl halide. Here's a fun one. What happens when the halogen is attached to a double bond? Well, a double bond, another word for a double bond is vinyl. So if someone says a vinyl group, they mean a double bond. Okay? So when the halogen is attached, they say here to an sp2 carbon, really it should just say to an alkene. Because you already know it's sp2, right? Because you're smart, right? It's sp2 carbon of an alkene, so it's attached to a double bond. So this is a vinyl chloride. If it was an iodine, it'd be a vinyl iodide. No problem, right? Not for you guys, right? And finally, when the halogen is stuck to a benzene ring, those are called aryl halides. Sometimes you hear people say aromatic halides. The proper word is aryl halides. And those are your 3 types. We're going to focus almost, I don't want to say exclusively, but almost exclusively on alkyl halides. The top one. Almost exclusively, we're going to focus on those. Pretty easy so far, right? Here we go. Polarity. You've heard me talk about it before. We're going to talk about it again. This is a big, crazy deal. Now, we learned about nucleophiles, yeah? Tell me what a nucleophile is, please. Ooh, try the opposite way. Try the positive charges, right? Nucleophile means nucleus loving, so positive loving, right? What's an electrophile?
It has a positive charge attracted to a negative charge.
Whoa, what?
That's what an electrophile is, right? It has a positive charge?
Not necessarily, though. Could be slightly positive, but yeah, it's attracted to electrons, right?
Okay.
Whew, you said that fast. Scared me. I was frightened. Yes, I think that's right. I'm confused now. Yes, electrophiles like electrons, right? That's what the phile part means, loving. Electron loving. So they're either, sometimes they're positive, sometimes they're slightly positive, okay? So now let's draw a simple alkyl halide, chloromethane. And we don't have to know the electronegativities of these things. We can kind of just guess at them by looking at the periodic table, right? We all know that, or we better know that fluorine's electronegativity is 4, right? Yes. And chlorine's just below it, so its electronegativity should go what? Up or down? Down. Should go down a little bit, right? So chlorine, I'm not sure the exact number, but I think it's right around 3.6. Not sure, it could be 3.5. But I do know carbon is quite far to the left. So its electronegativity did what? Went up or went down? Went down compared to fluorine, right? It's actually quite close to the metals, right? So it's actually quite low. It's like I think it's 2.1. Okay? It's either 2.1 or 2.4. I can never remember. I can never remember that one. Now, chlorine has a higher electronegativity. Is that true? So which way does the bond polarize? Towards the Towards the chlorine, right. So you guys all agree with me, this chlorine should be delta negative.
Yes.
That's not hard, right? This is general chemistry, right? And delta plus should go on the carbon. Is that okay with everybody? That's a big deal. It's a big deal. Why is that a big deal? Because now we know if we have a nucleophile, which, let's just say our nucleophile is negative. They're not always negative. Sometimes they're slightly negative. We know that this nucleophile now, when it attacks this molecule, certainly is not going to attack the chlorine. Why not? Right, so what does that do? They repel each other, right? Because what are the three things that have to happen for a reaction to occur? Collisions. Force and angle. Collision, angle, and force. I put them in that order, but whatever. You got it right. So if they'll never collide with the right angle, nor with the right force. So they'll never react. Right? They have to collide. Does that make sense? We know this nucleophile will probably attack that carbon. That carbon is positive. Slightly positive, I should say. We also know that this carbon can't accept 5 bonds, right? So this is going to leave, just like a leaving group, right? The leaving group, remember, we said, takes the bond electrons. Right? Okay. That's why knowing the polarity is a big deal. That's why knowing the delta positives, or where the real positives are. If you know where they are, you kind of have an idea where things are going to occur. Okay? Not too bad so far, right? Don't worry, we'll come back to that. Common names of your halides. Oops, sorry. Okay, you've all heard of chloroform, yeah? You know, you probably watched those old movies where the villain takes a chloroform rag and suffocates the poor damsel in distress. I can tell you right now that you suck in a bunch of chloroform into your lungs, that burns. And it doesn't knock you out right away, so you're probably going to turn around and kick the guy. How do I know? Been in this business a long time, and bad stuff happens if you do it long enough. Anyway, it burns really bad. It burns because it's not water soluble. So you suck it into your lungs, vapor, right? The vapor tries to interact with your lungs, but there's water coating your lungs, right? That burns badly. Now, whenever you have a carbon with 2 hydrogens and 2 halogens, that is called a methylene halide. A methylene halide. So if we had CH2Cl2, that's commonly known as methylene chloride, commonly referred to that. Just so you know, a CH2 group with anything attached to it, doesn't have to be chlorines or bromines, a CH2 group with anything attached to it, those are called methylenes. CH3 is methyl, CH2 is methylene. CH1 is methylene, just so you know. All right, next. Chloroform. Well, not chloroform per se. H3X, those are called haloforms. And here's your favorite. That's chloroform. Chloroform. If it had been bromines on that carbon, it would have been bromoform. If it was iodines, it would be iodoform. If it was fluorines, it would be fluoroform. And of course, CX4, that's called carbon, tetra halide. For example, CCl4, carbon tetrachloride. Carbon tetrachloride. And I forgot one. I'll do the easy one. These are called methyl halides. Whenever you have a halogen attached to a methyl group, it is called methyl halides. So now if we had something like this, CH3, Cl, that's called methyl chloride.
For the halioform, is the 3 supposed to be on the X, not the CH?
Which one? Oh, yeah, sorry. There you go. Pretty cool, huh? Am I going crazy or someone have a radio on? No, not you? Does anyone else hear that? Oh, that's you. Okay. That's funny. Normally I don't hear anything. Okay. All right. Oops. Well, yeah, we'll go with this. This slide's fine. We'll use this slide. Primary, secondary, tertiary. You've heard them before. Now they're back. And now these are interesting. You might want to pay attention to these. All right. Methyl halide, that's pretty obvious, right? A halogen stuck on a methyl group, methyl halide. So those are called methyl halides. Now, if you had something like this, CH3, CH3, if you just had that, you would have called that carbon primary, right? Right? It's primary carbon. So, if you put a halogen on it, that is a primary halide. It's a primary halide. One of the H's of the methyl is replaced by a halogen, so it's a primary halide. Because here it would have been a primary carbon, so it's a primary carbon here. That's how I do it. Some folks just say, okay, count the hydrogens, there's 2 as primary, but I think, be careful with that. Okay? So if it's a bromine, it'd be called a primary bromide. Iodine, a primary iodide. Get the idea? Okay, what about something like this? If you just had that, how would you describe that carbon? Secondary carbon, right? So if you had something like this, because up here it's a secondary carbon, so here it's also going to be secondary. This is a secondary bromide. See that? Everybody okay with that idea? Secondary bromide. Or if it was fluorine, secondary fluoride. Okay? Yeah. So there's 2 carbons attached to it. That's how I do it. I look at the carbons that are attached to it. You can look at the hydrogens too, but you've got to be careful when you look at hydrogens. All right, next. What's next? Tertiary. So there is a tertiary carbon, right? So what's this going to be called, do you think? Tertiary halide, right? Let's put an iodine on there for fun. There we go. So that is a tertiary iodide. So far, it's pretty easy, right? Right? I mean, it's just learning names and stuff, right? What's that?
They're not going to probably stay like that.
Oh, no, it's not that bad, actually. Bromide, yeah. Bromide. All right. So now these are all alkyl halides, right? So, is that carbon delta positive? Yeah, probably. This one too, probably, huh? Got a halogen stuck on it, so probably somewhat delta positive, right? So is that one over there. So they're all delta positive. So they all have the potential, maybe, of doing something interesting. Maybe. Maybe not. Types of dihalides. Geminal versus vicinal. I've put this question on my exams before, and I'm surprised some people always get it wrong. So like a 2-point question. Label each as vicinal or label them as vicinal or geminal, and people usually get them backwards. Geminal. The halogens are on the same carbon. That's considered a geminal relationship. When both halogens are on the same carbon, they're called geminal. I don't really know why. They just are. If the halogens are on adjacent carbons, that's called vicinal. It's called a vicinal relationship. Now, they don't have to be halogens. They could be nitrogens or oxygens or sulfurs or whatever. But their relationship to each other in the molecule can be either geminal or vicinal if they have this structural motif. And that's more of an, for interest's sake. We're not going to do much with vicinal or geminal dihalides. Go ahead.
And does it have to be two? Like, just like I'm comparing two halides?
Yeah, you have to have two groups to compare to.
So, like, for the geminal, it could be four, and be like, oh, all four are geminal.
You could have 4 bromines in one molecule and have 2 bromines on 2 different carbons, sure. But if you had 4 bromines on the same carbon, it wouldn't be geminal at that point.
Okay.
It would be just carbon tetrabromide. Still not too bad, right? We're luring you in. Write that down big. And in fact, start a new page. This deserves its own page. Write in nice big letters on the top of your page the S subscripted capital N 2 reaction. The SN2 reaction. Give it its own piece of paper. Write down beside the title, this is important. Write down beside the title, this is important. I probably should learn it right away. Because with the quiz on Monday, will probably involve this. Or maybe not. Unbeknownst to you, we've been doing SN2 reactions. We've done them twice, actually, in this class. I just didn't tell you. I left it as a secret. Here we have ourselves an OH. And you guys all know OH, hydroxyl, is negative, right? Hydroxide, excuse me, is negative. What are they using, iodide? We'll use iodide, too. Mix them together. Okay. One quick thing before I move on. I've written hydroxide and I've written iodide. They're both negative, right? You see how the charges didn't change from one side to the other? The other side, the left side of the arrow is negative, the right side of the arrow is negative, right? That's good. You keep the charges consistent, okay? Now, let me ask you a question. Is it possible for me to throw hydroxide in this reaction only? In other words, is it possible to have a negative charge by itself? No! What's probably the other thing that's in there?
Water.
No? Well, there probably is water too, but what's going to counter the negative of the hydroxide, do you think? Such as? Who? What? Well, I heard protons. I heard hydronium. What? What's a great counter ion to hydroxide that you all know? What? I can't hear you. That would be water. No. No. Look at the periodic table.
Sodium.
There's one.
Lithium.
Potassium, magnesium, calcium. One of them at least, right? Have to be in there, right? Are you all with me on that? Sodium hydroxide, most common base. Okay, so they're in there, yeah? I just left them off. Are you with me? Tell me you're with me or not. They're not written there. What? What's wrong?
Can you repeat
You understand that a negative charge cannot exist by itself.
Okay.
At all. Never happens. It's not allowed.
Okay.
So there has to be a counter ion in there somewhere to counter the negative charge. And that counter ion could be any positive thing, such as ammonium, calcium, sodium, lithium cations.
Okay.
They have to be there. So if you're going to make a reaction, if you're actually going to do this reaction, you can't add hydroxide. You have to add sodium hydroxide, lithium hydroxide, one of them. Okay? But I didn't draw it. I left out the counter ion. What's that called? Because it doesn't change from left to right. Okay? I have an ion over here that doesn't change over to over here. What's that called? No. Okay, let me just draw it. I have a sodium ion here countering the negative. Are you with me? I have the same sodium ion over here countering that negative. What's the sodium known as? No. $10.45. A who? No, it is a cation, but it doesn't get involved in the reaction. It's a spectator ion. Self high five. I will wait for you to do it. There you go. Close enough. Self high five. It's a spectator ion. It doesn't get involved in the reaction, so I leave it out. Why? Because it looks a little cluttery, right? So just leave them out. Now you can draw them in if you want, but if they don't get involved in the reaction, we just know that they're there. You know what I mean? So that's something you have to remember. So I have a negative on the other side. I have a negative on this side, and I understand that that negative is countered by some cation. I don't know what the cation is. Frankly, I don't care. What I care about is this. The hydroxide somehow makes a bond to carbon, and the iodine leaves the carbon as iodide. That's what I care about. That's what I have to explain. Are you with me so far? Now, this is the mechanism of an SN2 reaction. The hydroxide will attack the carbon because the carbon is delta positive. The iodine is delta negative. Is that okay? When it does that, the bond to iodine must break. Has to. Must break. Now, it's going to go through a transition state that looks kind of like this. Oops. So that's this transition state. The oxygen-carbon bond is being formed. The iodine-carbon bond is being broken. And then it will deliver products. Now, whenever I ask you to draw a mechanism, I'm looking for this. You don't have to draw the transition state. Okay? Now, if the question says, draw the mechanism and show the transition state, you'd want to throw that bad boy in there, right? But if I'm just asking for mechanism, I'm not necessarily looking for transition states. Now, in a question that I may ask you subsequent to that, the transition state may become important, and you should know, you'll know that it's important, and then you'll talk about it. But that's not very common. Usually, I just ask you to draw it. How many steps is this reaction? One. One step. Oxygen attacks carbon, iodine leaves. That's pretty cool. At the same time, at the same rate. The oxygen makes its bond to carbon at the same rate. The carbon breaks its bond to iodine. At the same time, at the same rate. Oxygen attacks, iodine leaves, at the same time, at the same rate. It's called a concerted reaction. Concerted means happens all at once. Okay? There is no intermediate. There's a transition state, but there's no intermediate. Remember in the chlorination reaction, we had that intermediate methyl radical?
Yes.
We don't have that here. We have a concerted reaction, which means it happens all at once. Iodine goes to carbon, makes a bond. At the same time, at the same rate, the iodine breaks its bond to carbon. So at no time did carbon not have an octet. Okay? Are you with me? Isn't that pretty neat? Now, I commonly refer to this with students, I call this the Disneyland reaction. And here's why. Did you ever go to Disneyland? This is not a commercial for Disneyland, by the way. They overcharge, underdeliver. And you go to the ride, and you're queued up for like an hour, and you're sweating, and you get to the front of the line, and the little boat comes in, and then you realize it's not a boat after all, it's a train. It's designed like a boat, which is weird by itself. And you get there, and then the doors open for you to walk on, and the doors open on the other side of the train for the people to walk off, right? You with me? So you start walking on at the same time and at the same rate as the people walking off. Don't you? And then you sit down, and the thing takes off, right? And then you come back around, and when it's time for you to get off the ride at the same time, at the same rate that other people are getting onto it, right? That's how Disney makes money, throughput. They just move you right along. Okay? That's an SN2 reaction. That's an SN2 type reaction. You get on as they get off at the same time, at the same rate. If you get on too fast, you're going to bump into them. If you get on too slow, people are going to be pushing you on, right? Because people can't wait to get on the Disney rides for whatever reason. Energy. Reaction. So the reaction progresses from left to right, right? We've seen these before. SN2 reactions. There you go. There's the hump. So one-step reaction, so there's one hump. Over here, we put ourselves a little hydroxide and our molecule methyl iodide. Hydroxide attacks the carbon, the iodine starts to leave. Up here, we draw our transition state like this. So there's our transition state, and then we fall down our cascade to products. And there you go. That's how it works. That's the reaction diagram. Much easier than that radical thing we saw, huh? Don't worry, it's coming back.
So is the energy at the end going to always be lower?
Not necessarily, no. Not necessarily, no. Typically, but not necessarily. I shouldn't even say typically. Sometimes. Now, what's the one question I haven't answered yet? What's the big glaring question that I hope you're all thinking like, huh? No, it could give you exothermic or endothermic. What's SN2 stand for? I just threw that out there. No one asked.
I thought you already would get on at the same time. Get on.
Exactly, yeah. Well, we don't say that to conferences and stuff.
Oh, you don't?
No, I would be more eloquent and speak with big words and stuff.
There's 2 full little words left.
I don't remember swearing, but okay.
Curse were the only full little words.
What does the S stand for, do you think? What's happening in this reaction? Isn't one group being replaced by another? Substitution. Very good. What's the N stand for? Nucleophilic, nucleophile. It's a nucleophile reaction. So there's a nucleophile in this reaction. Substitution, nucleophilic. What about the 2? No, not quite, no. Close. What?
Is it for rate?
It has to do with the rate, yep. Half.
Second order reaction.
Hold that thought. All right, what's it mean to be a second order reaction? And don't just say there's a 2 somewhere.
The concentration increases, the rate is increases as fast.
In 1046, you get an A for that. Well, what does that mean? What does that imply about the mechanism?
Twice as fast, which is twice as.
Okay, well, what does all this imply, though? What does all this mean? If I double the concentration of one, the reaction goes twice as fast, right?
Yeah.
If I half the concentration of one, the reaction goes half as fast, right? What does that mean? What does that tell me about the mechanism? If you didn't already know the mechanism, what would you deduce from that information? Say that what?
About the rate limiting stuff?
Yes, it is.
That the rate is, no, that's not like that.
Well, yeah, the rate does depend on how much you put in, but what does that tell you about the mechanism?
But what did she say? I couldn't hear her.
She said,
The rate limiting stuff.
The rate limit on how many stuff.
she was like next door to a self high five, but she stopped.
If you increase whatever this rate limiting step is, if you increase it,
Mm-hmm.
then
Increase what? The energy? Or
No,
increase the
the
concentration?
concentration.
Well, they've been saying that.
Second order rate.
It is second order. What does that mean? Yep, that's what everyone's been saying.
If you double or increase the secondary something.
What's it mean to be first order? And what does that tell you about the reaction? What the mechanism?
well, if you increase the concentration, you increase the likelihood of them colliding. Right?
That's true.
You
That's
increase
true.
the speed.
You will increase the speed.
So we can-
Like, it's in the one, this is loosely stated, but like
It's loosely stated.
No, it's like, relax, you know.
I am relaxed. I'm extraordinarily chill.
Yeah, okay. Like the first order, like independent to the concentration or something like one of them is like
It's independent to the concentration. It's dependent on the concentration of one reactant.
yeah.
Second order reactions dependent on the concentration of two reactants. So what's that tell you about the mechanism?
That is dependent on the concentration of two reactions.
Right? And what are the implications of that?
And what are the what?
The implications of that. You would have learned it in 1046 lab.
That because it's dependent on both reactions. If there's you said you already established rate concentration.
So one of the reactions is rate limiting?
No. Good guess, though. Try again. If the reaction rate is dependent on two different concentrations, what's rate limiting? Both of them. Exactly. They're both rate limiting, right? So that tells me something about the rate limiting step. What does it tell me? Just logically put it together. If both concentrations affect the rate, right? They're both present in the rate limiting step. Does that make sense? If the concentration of A and the concentration of B both affect how fast the reaction goes, they both must be present in the rate limiting step. Does that make sense? How many steps in this reaction? One. So they're both present in that one step. That's how I know that one collides with the other and goes through a transition. That's how we figured that out. Because we figured out, you increase this one, goes twice as fast. Increase this one, goes twice as fast again. Oh, well that must mean they're both present in the slowest step. Right? Can't be any other way. So SN2 means substitution, nucleophilic, bimolecular. Bimolecular meaning two things are in the rate limiting step. Right?
Right.
Isn't that neat?
Of course. Can you say that one more time?
SN2, substitution, nucleophilic, bimolecular. Some people say di, it's actually bi, bi. Two things are present in the rate limiting step. So here, this attacks that in the rate limiting step. This is the only step, so it's rate limiting, right? Okay? That's how I know both of these things are there. That's how I know. Because they both affect concentration. Sorry, pardon me. Both concentrations affect rate. Cool, huh? And in 1046, they would have told you that. But they tell you a lot of things in 1046, so you probably just forgot. Okay, we did that.
How do you know that there's not two humps equal rate? Like, how do you know that it's one and not two humps of equal energy?
Right, because you'd have to have an intermediate at that point.
How do you know that you don't?
Because if you had an intermediate, the next hump is always lower in energy because the intermediate's already at a high energy state, so it's pretty fast to get it over the hump. And there's other experiments you can do at that point as well to try to trap the intermediate and see if it's there. So if you ask me to prove it that way, I do two experiments. I would try to trap the intermediate with something that's very nucleophilic. When that failed, I would have good evidence to say that there's only one step in this reaction. Great question, actually. Okay, nucleophile strength. Uh-oh. You knew it wasn't quite so easy as just do that, huh? Nucleophile strength. Stronger nucleophiles react faster. Okay, that's all well and good. What's a strong nucleophile? Strong bases are strong nucleophiles, but all strong nucleophiles are basic. Whoa! Let's write that down. That doesn't make a lick of sense yet, but it will. Strong bases are strong nucleophiles, but not all strong nucleophiles are basic. Whoa! That's crazy talk right there. All right. Strong nucleophile. Let's just talk about the strong ones. First rule, anything negative. Anything negative is probably going to behave as a strong nucleophile. So hydroxide, for example. Cyanide, Cn-. Those are strong nucleophiles because they're negative. Okay? Now, you might have noticed chloride, bromide were in the moderate nucleophile list, and iodide is in the strong nucleophile list. That's peculiar. Keep that in mind. And here are your weak nucleophiles. Ignore fluoride. That's just weird. Look at these ones down here. Stable, non-charged molecules. Methanol and water. They're fairly stable, right? So they're not very good nucleophiles. Now, you can get them to react, and I'll show you how. But they're really, really bad at reacting. And they're bad at reacting because they're stable. They don't want to react, right? Because they're stable. Other things, like cyanide, for example, want to react. Now, let's look at this molecule right here, nitrogen. It's a nitrogen with a lone pair. So let's look at that. There we go. That's a pretty good nucleophile right there. Not too shabby. Now, why would it be considered a good nucleophile on the same level as OH minus? I mean, it's not the same level. I shouldn't have said that, but they're both considered good nucleophiles. They're both very reactive. It has to do with the fact that this nitrogen is delta negative. Right? It's got a lone pair, and it's delta negative. So those two things add up. Those makes it a pretty good nucleophile. You know what I'm saying? Does that make a little sense? Sulfur, S-, is also a good nucleophile. In fact, it's better than OH. Now, I want you to notice that. Sulfur, SH-, I just said was a better nucleophile than OH-. The one thing that makes it better, and it's kind of going to be a theme, like iodide, for example, follows the same pattern. It's a good nucleophile because it's negative, first of all, and it's big. Big things tend to be better nucleophiles. Let me say it differently. Larger atoms tend to be better nucleophiles. So S- is a pretty big ion, for example. So it's a better nucleophile than OH-, which is a small ion. Okay? Keep that in mind. We'll come back to that phenomenon. Just keep that in mind, okay? Size helps. Size helps. All right. So that's what you kind of got to look for. Now, it's going to seem daunting. It's going to seem intimidating to try to figure out what a good nucleophile looks like. But don't worry about it. Here's why. You're going to see a lot of the same ones because there's a lot of really common ones, okay? And they're all good nucleophiles. But before we get into too much more of that, I want to ask you one simple question. What is the difference between a strong nucleophile and a strong base? What's the only difference between a strong nucleophile and a strong base? No?
Nothing to do with like the conjugate acid?
A nucleophile is a Lewis acid.
Is that right?
What's a Lewis acid?
A electron acceptor?
Right.
Electron pair acceptor?
So you're saying a nucleophile is an electron pair acceptor.
Yes.
Okay?
So it's an acid, not a base.
Whoa, what?
I don't know.
I didn't hear what you said.
Looking for electrons.
So it's an acid
Hmm?
base.
Nucleophiles want electrons and then bases are negative already.
Right. What's the difference between a nucleophile, strong nucleophile, and a strong base?
One's already negative, one wants to be negative.
All right. For example, OH minus can be either one. That's a strong base and a strong nucleophile. What's the difference?
Is that how you look at it, like compared to the conjugate acid?
It's how you look at it. No, well, for example, OH minus is either a strong base or a strong nucleophile.
Yeah, but like nucleophiles could be more low. That's what it means.
No, but I'm saying that OH minus right there, I'm asking you to just consider OH minus. It's both a strong base and a strong nucleophile. Why? How can I say that, and how do I know which one's which?
Is it based on the solvent?
No.
Spectator ion?
No. What's an acid?
Electron pair acceptor.
What's a Bronsted acid? Proton donor. What's a Bronsted base? Okay. What's a nucleophile? So what? It's an electron pair donor, right? What's it donating it to? To a Lewis acid, right? To a Lewis acid. What's a Lewis acid? Electron pair acceptor. Okay? So, an acid, think about Bronsted acids. Bronsted acids donate a proton, right? Bronsted bases accept protons, right? So if a base attacks a proton, it's a base, right? What if my OH minus attacks something else, say carbon? Would you call it a base? I sure wouldn't call it a Bronsted base, would you? It didn't attack hydrogen. It attacked a carbon or non-hydrogen, right? So the only difference between a base and a nucleophile is what's being attacked. See the difference? Bases attack protons. Nucleophiles don't. They attack other atoms. So hydroxide can be either considered a strong base or a strong nucleophile depending on what it did. Does that make sense? In the first example of the SN2 reaction we saw, OH minus, which you all should have said was a base, behaved as a nucleophile. It did a nucleophilic reaction. It didn't attack a hydrogen, it attacked a carbon. Are you with me? Because a nucleophile, if you want to go back to Lewis theory, electrophile is a Lewis acid. It is. It accepts a lone pair. But isn't the proton a Lewis acid too? Doesn't it accept the lone pair from the hydroxide? They're the same. It's just depending on what's being attacked, right? If you attack a hydrogen, you're a base. A proton, pardon me. If you attack a non-proton, you're a nucleophile. So it's all about who's being attacked. Are you with me? So let me ask you a question then. If you threw this molecule or this ion in with a molecule that could either be a nucleophile or an acid, which one's it going to do? Or is it going to do both? It's going to do both. Chances are it's going to do both. You with me? See where we're getting here? We're getting some complications now. Neat, huh? I'm telling you, this course is fun. All right. And here's the slide that kind of talked about what we just talked about. Trends. All right. This top one's easy, right? Neutral molecules are not as good as negative ones for acting as nucleophiles. So, for example, water, compared to OH minus, water is not a very good nucleophile. It doesn't attack things very often. Because O minus is much more negative than O delta minus, right? Right? So it's going to attack faster. Same thing here and here. Same thing for these two. Now, nucleophilicity decreases from left to right. Decreases from left to right. Oh, these are mixed up, by the way. These should be down here. Should be up there. Sorry, these examples should be up here. From left to right. So this is more nucleophilic than that, and this is more nucleophilic than this. F minus is a terrible nucleophile. It's a good base, though. Okay? So as you get smaller, you become less nucleophilic. But you become more basic. You become more basic. Okay? So the bigger you are, the more you're prone to be a nucleophile. The smaller you are, the more you're prone to be a base. So O minus, which is smaller than NH minus, is going to be a base. Are you with me? I'm talking about atomic size, neutral atom size. Okay? All right. Increases down the period. So size increases. So, if you look at the period, chlorine and bromine, for example, are high up on the table, right? So as atoms, they should be quite, well, they're large, but they're small compared to iodine. Iodine's at the bottom, right? Iodine is huge. Are you with me? So now we have to talk about something that's going to kind of maybe challenge your mind a little bit. It's this idea of polarizability. Now, think about iodide, I minus. It's got how many electrons? 54 electrons, I minus. Those electrons are circling around the neutrons, or they're somehow around the nucleus, right? And it's large. So those electrons on the valence shell of iodide, they're being shielded pretty efficiently by the core electrons, right? The electrons that are between the nucleus and the other electrons, the core, it's being shielded by the ones that are in there, right? So the ones on the outside have what's called a very low effective nuclear charge, right? Remember all that from general chemistry? Effective nuclear charge? So those electrons on the outside are not that strongly held. Are you with me? So think about iodide as a big fluffy pillow. It's fluffy. Okay? Seriously, think of it as a fluffy pillow. Now, if you take a big fluffy pillow, you can push all the stuffing to one side, can't you? Okay? Or you can push it all the other side, can't you? That's called being polarizable, right? You can move all the filling to one side and have an empty other side, right? Delta minus, delta positive, right? Things that it can do that, like big things like iodide and sulfur, they can polarize. They're polarizable. Are you with me? Things that are polarizable are more nucleophilic, less basic. Iodide usually never reacts as a base, but it's a very good nucleophile. Why? It's polarizable. Now, we'll come back to that understanding of polarizability later when we get into more different SN2 reactions, but that's an important concept, polarizability. Fluoride, on the other hand, the very top of the halogens, F minus, is a very small ion compared to iodide. It's extremely small compared to iodide, right? So now imagine your pillow is very, very tightly wound. All the stuffing is compressed hard into one small area, just like fluoride does with its electrons, right? It sucks them in, right? So imagine fluoride is not fluffy at all. In fact, it's downright hard. Okay? You can't move those electrons around very much to one side or the other because they're held very, very tightly. Non-polarizable. Okay? Fluoride's a terrible, terrible nucleophile, but a pretty gosh darn good base as far as weak bases go. Never use fluoride as a base, by the way. It causes bad problems. Now, this whole thing I've just described to you is actually an advanced topic in organic chemistry, but you guys can handle it. It's called hard, soft, acid, base theory. Hard and soft. So what do you think's soft? The polarizable ones are called soft because, they're fluffy. The hard ones are small and the electrons don't move around very much. Okay? Fluoride is hard. Okay? Soft things, polarizable things, are very good nucleophiles. Hard things are not quite so good. They're better bases. Okay? Which is why OH minus is a better base than it is a nucleophile, because it's not very polarizable. Nitrogen, on the other hand, is starting to become more nucleophilic and less basic. Are you with me? Go down the periodic table. Start getting more bigger atoms, more polarizable, more nucleophilic. Now, be careful. That doesn't mean that none of these nucleophiles, all of these nucleophiles can behave as bases under the right conditions. Because remember, a base attacks a proton, right? Are you with me? And one more thing. Remember, these things aren't thinking. So a nucleophile doesn't go into reaction thinking, I'm on the lookout for positive carbons. It doesn't think that. It's on the lookout for positive. For delta positives or positives. That's what it's after. And it doesn't care if it's a hydrogen or a carbon. Okay? As far as this is concerned, it's just positive. You with me?
So the nucleophile doesn't care? Or just
How it can't, it doesn't think. So it can't care. It's only reacting to energy. Are you with me? So if you have a nucleophile with two different nucleophilic centers, both are delta positive, you could get reactions at both, right? Because remember, they don't care. They just react to energy. All right, so here's a little picture of the polarizing effect. You don't have to draw this, just kind of check it out. Here we have our fluoride, which is considered a hard ion. When it attacks the back lobe of this sp3 orbital right here. Remember the sp3 orbital had that little lobe in the back we very rarely drew? Remember we showed you that? This fluoride has to attack it. It has to put its electrons in that orbital. It has to shove them in there somehow. Okay. Now imagine if you're trying to say, well, let's do this one. Imagine you all go to dinner, like you and some friends, and all in the same check, right? So what happens to people when the check comes? They become very hard, right? And their arms come tight to their chest, right? Try to reach for that bill, but they get, the alligator arm, that commercial on TV? They get the alligator arms, right? That's the stingy ones. They don't want to share. They don't want to give their electrons away, right? But then there's the people that got a lot of money. Their arms go, oh, I'll pay, because they're very soft and fluffy when it comes to spending money, because they got a lot of it, right? Or they pretend they do, right? So someone that's hard, their electrons, my electrons, can't get into that lobe because I can't push them in, because I'm attracting them back, right? I'm trying to push them into the lobe, and they keep coming back to me because I'm hard. Soft. Completely different story. Those electrons that are going to react with the nucleophile are quite far from the protons. So to donate them into that lobe, remember that carbon is delta positive too, right? Put them in that lobe, the carbon actually draws them in. Because the carbon is delta positive. Are you with me? Isn't this neat? This is how it works. Yeah, I know you guys all hate it, but it's okay. You'll learn to love it one day. December 14th. Good for you for getting that joke. All right? So soft things, big things are more likely to be nucleophiles. Hard things are more likely to be bases. Okay? Because of polarizability. Read that on your own. Command it so you understand it. Okay? And if you don't remember the alligator arms. Or you can do my old trick. When the bill comes, got to go to the bathroom, right back. Then send a text. I'll meet you in the car. Solvent effects. Probably the single most important thing that you can think of when you're thinking of SN2 reactions is you look at the solvent. You look at the solvent. One more time. Look at the solvent. Because only certain solvents are good for SN2 reactions. The other ones are not very good. Okay. Yeah, look at the solvent. Now, let's discuss, shall we? I need like 6 people to come up to the front. Don't all jump at once. Careful, don't hurt each other. 1, 2, 3, 4, 5. 5? Is that still 5? I'll be the 6th one. That's okay. All right. So now, you all are solvent. You are the electrophile. I am the nucleophile. Now, here's the deal. I'm negative. Okay? You're positive. You all are polar protic. Now, don't worry about what that means. Think water. Think water. Water is delta negative and delta positive, right? So if I'm positive and they have negative features, right? Aren't they going to surround me? So go ahead and surround me. Go ahead. Just everyone, come on, up front. Here you go. Some folks get in the front. There we go. There we go. Come on, close it in. There we go. All right, because they're all attracted to me because I'm the opposite charge, right? I'm negative. They're all showing me their positive sides, right? Now, you're positive too, right? and I'm negative, but now I'm like, this environment feels pretty good. I think I like it here. Yeah, I like it here. Feels pretty good. My energy's come down. I don't even know that you're out there anymore because I'm surrounded by a positive charge. This is kind of nice. So what's my motivation to break through this and go react with her? I have no motivation at all. I'm completely content. My energy is low. Why is my energy low? Because they all have the opposite charge from me, and I'm like, kind of like this. This feels kind of nice. So now I'm not going to go react with her. Or if I do react with her, it'll be very slowly. Because I got to break through here and and then we have to collide, right? Then I have to find you, right? And don't forget, if I break through here, there's other ones that are out there between me and you that are going to prevent me from getting there. And oh, by the way, she's surrounded too. Because she's positive, right? The water is going to show her their negative side, right? And she's going to be like, you stay over there, positive charge. I'm good. I don't need you. I'm content. If that happens, SN2 reactions stop. Why would they stop? Everybody's happy. Are you with me? Our energies are all low. There's no motivation to react. So, an SN2 reaction can't have solvent like water. It's got to be a different solvent. One that doesn't do this, that doesn't surround the nucleophile and the electrophile. It can't be there. If it's there, reaction goes very slow. So we've got to change out the solvent. So water has to go away. Polar protic solvents. Okay? Does that kind of make sense? Thank you to my actors. They're awesome. Okay? But don't forget, not only was the nucleophile surrounded by the solvent, so was the electrophile. Everybody got surrounded. Okay? It's called solvent caging. Now, do we have time for one thing, or do we get to stop? All right. Let me show you an example. A very simple example. You guys all know this to be true, right? You guys all know that's true, right? Yeah. Sodium chloride dissolves in water, gives you sodium plus and aqueous and chloride minus, right? You probably never thought of this before. Maybe you did. The reason why sodium chloride can dissolve in water so fast is because the sodium and the chloride get what's called solvated. And solvated means surrounded by solvent, essentially. And keep in mind, if you try to melt sodium chloride, like just take a torch and melt it, it takes a lot of energy to melt sodium chloride. A hell of a lot of energy. But you put it in water that's near freezing, and it dissolves. That's impressive. And that's because the water, these are delta negative, right? The delta negatives of a bunch of water surround the sodium, mimicking the chlorides. They mimic it. They bring the sodium into solution, and the sodium doesn't really notice a difference between that and chloride, right? There is obviously a difference, but the energy difference is not great enough to prevent solvation, right? Same thing for this chloride, only now it's the hydrogens that are facing it, right? And there's more than just that, but I want to stop. The hydrogens are facing the chlorine. They're mimicking the environment that the sodium gave the chloride. So now these two ions are in solution, and they're solvated. Their energy is low. They have no impetus to react. There's no driving force, right? Because you've given them a stable environment. And these things are called solvent cages. And in organic, we call them solvent cages because they literally put the nucleophile in a cage. So the nucleophile can't attack. Okay? Say that again? I can't hear you. I'm sorry. Yeah, they prevent the nucleophile from being able to attack anything because they surround it and prevent it from wanting to react. So we're going to have to talk about this next class, about what we can do to prevent this from occurring so that our nucleophile wants to do what we need it to do. Because remember, the goal of an SN2 reaction is to actually make something new, right?